Hi, how's that? Excuse me, I've got a bit of a cough, so I hope you all enjoyed your lunch. I certainly did. Just to keep you awake after lunch, I'm going to talk about schemas and schemaless when we're not under attack. So what we're really talking about here is how you move from one version of an application to another version. Now, when relational databases were invented, they kind of imagined that you were going to design your application and then basically never change it. And that was a really bad idea. And over the intervening years, we've realized that applications need to develop very quickly to stay on top of business requirements. And so that then presents the challenge of how exactly we can change the underlying database schema. Now, sometime in the early 2000s, a movement arose called NoSQL that advocated a schemaless approach to data. And one of the reasons why that approach came about was because relational databases did not really correctly address the topic of schema change within the database. And as a result of that, people looked for ways to avoid using database schemas altogether. Now, where we are in the present day is Postgres, and probably other ones as well, have gone to a lot of trouble to make schema change within your database much, much easier. And what I'd like to do in this presentation is explain how that works, the options that you've got for schema change, but also to contrast that against the actual schemaless approaches and the way that that would work as well. Difficult to do all of that in 40 minutes, but I'm going to try. So the first thing to realize is that Postgres DDL is actually transactional, which makes it a lot easier to enact certain types of changes in your database. I say easier, I don't use the word easy, because there's some challenges along the way that you need to understand. The first of which is that there are some DDL operations that you can't execute within a transaction. For example, vacuum or create index concurrently can't be executed within a transaction. That's because the way that create index concurrently works is actually to execute 3 separate transactions while that command progresses. So there's a possibility we might change that in the future, but really for now it's difficult to make that transactional. So the first thing that we need to understand about DDL operations is the type of locks that are taken by different types of operation. So for creating a table, as you might expect, we need an access exclusive lock, which is what Postgres calls the highest level of lock. Access exclusive, meaning you can't even read the table while this is executing. And that also applies for drop, as you would expect. You wouldn't expect to be able to read the table at the same time as it's being dropped. Now, alter table is different because alter table is executed potentially while there's a stream of changes against the table. And so we need to understand that some operations do require a complete lock on the table, but many operations don't require the full lock. And what we're going to do is look at the fact that some operations need a much reduced level of lock. Guys over there, if you want to come across, there's actually a few seats over here and a few seats there. So if there's going to be some more people join, then there'll be no room at all there. So may as well interrupt the video now than interrupt it later. So there's a difference between create index and create index concurrently. Create index takes what's called a share lock on a table, and that prevents you from doing any write operations against the table. Obviously very restrictive on a production system, and so that's why we invented create index concurrently, and now there's drop index concurrently and re-index concurrently. So the way that locking works is actually going to be covered in some detail by my colleague Abhijit, so I recommend that you attend his session as well. But just to mention a couple of points about that, by default, locks wait forever, which means if you issue a DDL statement and it happens to wait behind a long-running select statement, then the DDL operation that you thought it was going to be a nice quick operation could sit and wait for hours behind that select statement, okay? So even if the operation itself runs in less than a second, waiting for the lock might take hours, okay? So the actual lock waits is important to understand as a DBA, and that's one of the reasons why we have a parameter called lock timeout that allows you to specify that you don't want to wait forever, given that forever is quite a long time. There's some other best practice that comes out of that, in that you should try to run your DDL at quieter times. Now, that's a ridiculous statement, I know, because a lot of people are running 24/7 websites, so what on earth is a quieter time, okay? Well, there may not be one, but if there is one, it might require some assistance from the application itself, where you're actually turning off parts of the application or constraining them in order to run the DDL. So as a DBA, it's no surprise to imagine that if you start executing DDL on a system and the application team have got no idea that you're doing it, it's going to fail, okay? And that's really where DevOps comes in. The developers need to be aware of what's happening in the operational database. Otherwise, you're going to fail. The other thing that you need to think about is the duration of DDL operations. Duration meaning how long will it execute for, okay? So a create table operation is a fast metadata operation. What I mean by that is it's the type of operation that only makes changes to the database catalog. It doesn't involve extended operations on the data itself. So for example, drop table, when we drop a table, it's fast against the catalog, but we actually have to search shared buffers to see if there's any data blocks from that table in shared buffers. So there's a slight but noticeable delay. If you've got 32 terabytes of cache or whatever it is you're running with these days, it's got to search all of that before it drops the table, okay? So that does or can take an extended amount of time. Create index, for example, always needs to scan the complete table, even if you're building a partial index. And as you might expect, therefore, the bigger the table is, the longer the create index will take. And that's one of the reasons why we use partitioning, because partitioning then allows you to split your table up into similar size units, and that puts a maximum duration on the execution of the DDL operations. Okay, that's a particularly useful thing. And alter table is again a source of complexity, in that some operations are fast metadata operations and some are very slow, needing to scan the table. And there's also some operations that lock the table completely and rewrite every single row in the table, okay? So just because it says alter table on the command, it doesn't mean it's going to execute fast or slow. What you need to do is understand the difference between those types of operation. Excuse me. So just to explain that in more detail, excuse me. If you add a column and that column has got a default of null, then that's a fast operation. And in Postgres 11, we enhanced that that if you added a column with a default value, that could also go quickly, okay? Drop column is also fast, but it's fast because it doesn't remove the data from the table. We just tell you to ignore it. So when you scan the table, it's still looking through rows that contain that data, and it's only until later that you see a way to remove that data. Now again, altering the data type of a column is something that can be fast or it can be slow, depending exactly on how that works. So if you were doing something called a binary coercible change, that will be fast, and otherwise it's slow. Now, of course, let's have a show of hands. Who knows what binary coercible means? I'm not really sure if I do. Jim claims he knows. We'll test later, but no, okay. So, very honest, thank you very much. Assuming you're not just asleep. Okay, good. No, not asleep. So, what does binary coercibility mean? Well, the first thing to understand is that it's actually a one-way operation. So, if we move from, my example there is a column called description that's defined as varchar 1 to 8. If we move from varchar 1 to 8 to varchar 20, that is not binary coercible, because quite clearly, if you've got 128 bytes of character data, that's not going to fit into 20 bytes, okay? So that doesn't work, okay? What does work is if you go from 128 to 256. Now, in that example, every single 128 character string will fit inside a 256 character data type. And as a result, we're able to just magically say that change has taken place, okay? So the binary coercible one is quick, and the binary non-coercible one is slow. So another example of that is a change from integer to big int. Now, a lot of people have, when they first define their table, they put a key on the table and they define it as an integer. And then as the database grows, they go, now I've got to replace that with a big int. Well, obviously an integer is 4 bytes and a big int is 8 bytes, and there's no way that you can make one work inside the other. So that's not binary coercible, and it causes a complete rewrite of the table. So let me just remind you again, the rewrite operation will fully lock the table, and it will rewrite every row in that table. So if you've got a 1 terabyte table, then that is going to run for a very, very long time, okay? So you'll probably be sacked if you try to rewrite your 1 terabyte table, whereas if you do a binary coercible change, you'll get to keep your job, okay? So kind of useful information to understand, right? So make sure you think about the type of change that you're going to make. There are ways to test this, but the most important thing is that you understand those operations before you make those changes on a production system. I say that because we experienced last week somebody making a change they hadn't tested on a production system, and obviously that causes difficulties. So one of the things that we've been working on within BDR, which is 2ndQuadrant's distributed PostgreSQL. Yeah, hi. Because of the way that we do packing, it's not necessarily possible to make that work. I agree conceptually it could be possible that there was padding in the row that would allow you to make that change, but at the moment the test does not include that insight in the code. It just tests whether it's binary coercible. So what I might do is nod to the fact that it's possible that such a rewrite might be achieved without rewriting the table. And I've recently made a list of all of the ways that we could improve alter table and gave that to my team so that we can potentially think about improvements in the future. And that exact case was on the list. Okay, so it is potentially possible to change that in the future, but right now it rewrites the whole table. Thank you. Sorry, I can't hear what you're saying.
Can you please repeat your question?
A time series.
Type theory applied to types? For example, when I work with a language like C or Java, I have a zoo of types through which I can, cast.
I'm not really understanding what you're saying, but I think the answer is no. Okay. So, yeah. So what, I mean, in terms of what we plan to do in the future, as I said, I've just literally 2 days ago made a list of all the possible ways that we could improve the alter table command, and including tables that mix different row version types within them was certainly one of them. And I think that might be what you're suggesting. So yeah, there's certainly room for further improvement in Postgres. Much of what I'm telling you is a journey that I've been on for the last 10 years to improve locking strategies and improve the way that we do things. A recent change in Postgres 12, for example, was an improvement that allowed you to change timestamp into timestamp TZ data type, which had previously been a rewrite, and that was optimized in Postgres 12. So every release, if you look through the release notes, we are improving the way that this schema change works. What this slide was about to be about was BDR, because one of the things that we built into BDR is the ability to have different database schemas for the same table on different nodes. And what that allows you to do is something that we call a rolling database schema upgrade, where you can actually change the table one node at a time in your cluster as a way of upgrading your database. So BDR isn't just about high availability, it's actually about system and schema upgrades as well. I'm not going to talk any more about that here, but I just wanted to mention that that's one of the features in there. So there's other actions that we have within alter table. It's possible to enable and disable triggers and set various things like statistics information. Now, all of those operations are metadata-only operations, but the trigger, for example, will take a share row exclusive lock, which blocks writes, whereas the other actions take a share update exclusive lock, which doesn't block writes. So that allows reads and writes while it executes. There's different lock types held for partitioning, in that when you attach a partition, it will lock the actual partition fully that's being added. But as of Postgres 12, thanks to Robert, we've now got a share update exclusive lock on the parent table, which means that we're allowed to do reads and writes against other partitions, but we just can't do other DDL while that's executing. When we detach a partition, we haven't yet worked out a way of using anything other than access exclusive lock. And as yet, we don't have a good way of coalescing partitions. If we did, I'd be worried about how long the locks were held and that kind of thing. So again, some further work to do. What some people are not aware of is that alter table has got an optimization that allows you to make multiple changes in one statement. And that actually optimizes the number of scans of the table, which makes it extremely efficient for production use. So there is some optimization in there already, and as our friend mentioned, there's potential future optimizations as well. One of the things to watch for when you're making a load of changes is if somebody sneaks in a create index statement in the middle of what you thought was going to be a short change, because the alter table statement is a metadata only operation and is quick, but the create index statement is not optimized, and it will scan the full table. So that transaction will run for a long time. So you need to be careful to inspect your DDL to make sure that it works effectively in production. There's another trick that you can use called not valid, which is when we add constraints to a table, you can request that the constraint is not validated. Now, if it's not validated, that means that you don't need to scan the table, and what that means is that the execution time of this DDL will be much reduced, like 1 second rather than 1 hour. And now after we've added that constraint, we can always come back later to execute a validate constraint operation. Unfortunately, you can't do validate all constraints. You have to name them one by one, but you can do it in one pass of the table. Now, the good thing about validate constraints is that it runs with a share update exclusive lock, meaning that you can run it while you're doing reads and writes against the table. So if you split your DDL operations into two, the locking characteristics are greatly improved. So what we're talking about here really is DevOps for database, what some people call application release automation. The key concept in doing this successfully in production is, in my opinion, to use scripts and code and not to use GUI tools because I guess it's famous in my mind, but I once said to a customer, yeah, let's just click on that. And while I was with the customer, I clicked on it thinking that it would be a fast operation, and it wasn't. And the whole database locked up and everything stopped, and I was severely embarrassed. But, you know, we make mistakes, but the point there is that if you just point and click using a GUI and imagine that that's magically going to work, it magically works, but it doesn't stop it from locking up everybody else on the system, okay? So you need to think about infrastructure as code, think about automatic testing, and reproducibility of bugs. You know, when people say to me, our system's gone wrong, and you say, well, what did you do last? And they say, I don't know, then that's not very useful. It's not really going to lead to problem solving. Hi.
Just a minute.
There's also a product called Liquibase that helps with the execution of DDL, which is what they coined the term application release automation. Yeah, please go ahead.
So does Liquibase work with all the databases, or it's very restricted?
Liquibase at the present time doesn't support all of the optimizations that Postgres can utilize. But I'm hopeful that it can be changed to do so. Other than that, it's quite a useful tool for being certain about the way that you roll out your DDL onto a system. So, but that's, you know, potential future optimization as well. So anyway, useful. Okay, so that's the current state of affairs with managing your schemas. What I'd like to talk about now is operating your database in a schemaless manner. So the basic support that we have for a schemaless approach is to use document-centric data types like JSON or XML data. And obviously, if you're using JSON, then the best implementation is to use the JSONP data type, because that's better for rapid access. And if you're using JSON data, then you can use one of the advanced index types that we've got. For example, the GIN index is suitable for use on JSONB data. And that approach you have there allows you to add new fields to your data without executing DDL. And that's why it's called schemaless. So if we insert data into the measurement table, you see here I'm inserting a key of temp with a value of 23.5, and then on the very next insert, I can actually invent a new field and use that immediately within SQL. Now, the good thing there is that I'm able to use the new field automatically, and also the new keys can be automatically indexed. So no DDL of any kind in order to introduce that type of change within your table. Now, that's great, but my view on that is that the regularity of your data within the database actually is effectively just a different kind of schema. And that requires you to manage that as well. And what I actually wanted to mention is that Ivan is going to give a very good talk on practical use of JSON. And so in this talk, I'm not talking very much about the capabilities of managing JSON data. Whole talk on it. It's going to be a good talk, so make sure you go to that one, please. Okay? I'm going to be talking about the difficulty of managing data as it gets progressively more complex within JSON. And what I'm saying is that as you invent new keys within your data, managing that becomes a more difficult process, because if I send an email out to my fellow developers saying, guys, I've just invented this new key, it's called Sunny, and you can use that immediately in the application, and they misread it, and they think it's actually called Sun rather than Sunny, then I'm inserting data with Sunny in it, another guy's inserting data with Sun in it, and we both think the data's the same, but when we search for the data, actually we don't find the data that we're looking for. And that then leads to data quality issues within your database, because data you thought you'd inserted with one data value is actually stored on a different key. Possibly, and I'm going to talk more about that as well. So I'm not just bad-mouthing this, I'm talking about the potential pitfalls of this particular approach. One thing that, just to note there, is that depending on the length of the name for the key, when I used the key sun, it was shorter than temp, and so JSONB actually puts that first in the implementation. So the order of execution or the order of placement of the keys can change depending on which key values you use. So there's some differences there. So what I'm saying is that there's potential to introduce data quality problems into your database unless you enforce some kind of strict management. Now, obviously, if there's an application layer that's going to enforce what those keys are, then that's good. But what I'm imagining is that there's a database where there's multiple applications acting against it, and sometimes we want to change the way field names are called. Sometimes we want to coalesce values. So over time, the data in the database can get quite complex unless you manage it in some way. So one of the things that we can do in the database is actually say a query to say what keys are in use in the data. And the purpose of doing this is so that we can look at the list and see if there's some keys that we don't want in there anymore, maybe want to rename them, move them out, delete them, whatever. Okay? So these are some techniques that we can use to do that. So once we've identified keys that we don't like, we can then issue some queries to find rows that have those key values. And in the situation here where I have decided that actually I only want two key values, one called temp and one called sunny, I can then execute a query that retrieves the data that's got those field values, or I can search for the other way around. I can bring out the data that doesn't have those values, so not in the list of key values that I want. So this is a technique you can use for finding irregularities in your JSON schemas. That's a great question because it's not. And the current function that's on my list of gotchas is that JSONB object keys is not recursive, so it doesn't descend a hierarchy. So when you've got hierarchical JSON data, it is much more difficult to search within it. Anyway, because I'm a database guy, I want to put constraints and reference checks inside the database, not inside the application. Okay, so there's a movement ongoing now called JSON Schema. The idea is to invent a way of specifying that the JSON in your database should be regular, so that you can come up with a strict definition of what the database should contain. And that is an example of a JSON schema that I've written specifically to enforce my example. I know it's a trivial example, but that's a valid JSON schema. And then we can actually enforce that schema within our database using some validation logic. We can actually have a check constraint on the JSON column that enforces the JSON schema. And there's actually two examples already available that allow you to enforce a specific schema within your data. One is written in PGSQL, which means it will install on your favorite clouds. And the other one is written in C, which makes it a little bit more challenging to install, but it's actually a lot faster to validate your JSON data, okay? So what I'm saying is that if you use JSON in an uncontrolled manner, it could cause problems for you, but I am recommending that you use your JSON data in a structured manner and that you think about enforcing constraints upon that data. And I guess with a slight smile, I say that's where it stops being schemaless and it's actually just a different kind of schema, okay? So I've got a slide on JSON gotchas, but I'm certain that that's going to be covered in more detail, so I won't go into that here, other than to say there's a couple of things that you need to think about. I am not bad-mouthing JSON. It is perfectly valid to use in your PostgreSQL databases. What I'm trying to do is present information for schemaless and schema approaches so that you understand that there's pros and cons to each approach, okay? And I'll just slip straight to the conclusion there, is that both approaches can coexist happily within the same table even, let alone the same database, okay? And that is really one of the big strengths of PostgreSQL, is that we allow you to mix different types of data within your database. So we're not prescriptive. We don't say you must use JSON, but we don't say you must not use JSON. What we say is you can use either and you can mix and match it in any way you choose, okay? And that is what is really powerful. I do have to say that certainly in researching this talk, I found some problems in the implementation of JSONB, not bugs, but possibilities for future improvement. But like I said, I also found some possibilities for future improvement in the way that we do alter table, okay? So as you might expect, there's going to be roadmap items on the Postgres development schedule for many years into the future. So what I wanted to do here is actually refer to a real-world example of the use of both of these techniques inside a single application. And I received the permission of Moodys Analytics to describe the way that they have used their PostgreSQL application. So the latest version of the application called CreditLens runs only upon PostgreSQL. And the reason for that was multifold. Obviously, they were migrating away from other databases, but the CreditLens application itself is managing lots of disparate types of information. And it's quite important in that world that the different types of information are managed correctly. So when you're managing credit data, that data is coming from an array of sources, okay? And so it's very complex, and it needs to be structured in regular ways, but also flexible ways. So what we have within this application is that within the application itself, you can actually specify user-defined fields that enhance the definition of that database for that implementation. And because of the way that PostgreSQL is written, there's a menu option that allows you to add a field to the database, and then that generates an alter table statement, and then it will be executed for you. So it's not a DBA operation to enhance the database, it's just point and click to actually add user-defined fields. And because the alter table statement is adding a column, it operates very quickly and easily with no DBA impact at all, okay? And so that's a great example of how we've managed to bypass completely the DBA in terms of adding flexibility to the application. So that's the first usage of the PostgreSQL techniques. But also what happens within CreditLens is that additional user-specified data is held within a load of JSON data tables. And by isolating that data into a small number of tables, we get two things. First of all, we get the flexibility from being able to add new data fields easily. So both Moodys and Moodys customers can add new types of data to the credit reference application easily. But when it comes to upgrading the application in place, that's also easy to do because all of the configuration data is held in one place within the JSON, okay? So that's two examples of how within one application we can actually use the modern features of PostgreSQL to great advantage. And what that means is that CreditLens only runs on PostgreSQL. Now, I fully support the idea that applications can and should be written in a database agnostic way, but where there's advantages to exploiting additional features in Postgres, then that's where I certainly encourage people to do that. And I think this is a brilliant example of all of the features being used all at once. So thank you very much to Moodys for giving permission to mention that on this slide after conversations that I had this morning. So thank you very much. Yep.
Excuse me?
I'm sorry,
Just a
I
minute.
can't discuss in any further detail the contents of Moodys applications. You can speak to them, but I can't really. Actually, I don't have many more details, but if I did, I couldn't share them with you. So,
Simon, one
Yep.
question about schema JSON.
Yep.
How do you update that schema, and how is that different from updating a column in a table?
Well, that's a great question, and I do have a slide on it. So thank you for asking that. So one of the difficulties with enforcing any kind of constraints within the database is If you invent a new constraint, then you have the difficulty of, do I implement that constraint on all of the existing data, or do I just implement the constraint from now onwards? And that's one of the differences that you get with adding a check constraint where you add it as not valid, okay? But that's not particularly satisfying. So my solution to the problem is to actually have a schema version column on your table, and then when you choose to implement constraints, you can actually implement the constraint as saying, for rows that have schema version 5 onwards, we can implement this check constraint, but for earlier versions, it's okay for them to not be compliant. And that technique works with both standard relational data and for JSON data. So if you actually implement new versions of the schema, you can always do that in such a way that you're only implementing the new schema from a certain version upwards. So that works, but the general rule is if you're relaxing a constraint, it's easy. If you're tightening a constraint, it's hard. Okay, that's the sort of general advice about what to do. I do need to stop talking at some point on the subject, but I'm happy to take further questions. So what my summary of this is, PostgreSQL is very powerful and it allows you to have both fixed declared schema approaches and schemaless data within the same table if you want it, or in separate tables if that makes sense to you. And both types of data are supported properly with good, fast executing DDL and multiple types of indexes that properly support those data types. So it gives you a wide range of options when you're designing your PostgreSQL databases. So thank you very much.
Thank you, Simon. Any questions?
Yep.
Excuse me, I would appreciate if you raise your hand before asking the question.
If only because I can't really hear you otherwise.
So there's this concept in PostgreSQL been there for ages called foreign data wrappers.
Yes.
That means if you see a limitation in particular functionality, you can always write in a wrapper which links in as part of the instance, right? So when, for example, you talked about that JSON copy recursive, I don't really see that as a disadvantage for the simple reason it defines as a starting point. If I apply the JSON path library,
yes,
I can say do the search from level 2. I might find my key. Do the search from level 3. So I'm doing still a flat search. It's just that my starting point shifted, thanks to a foreign data wrapper.
Well, yes, the main difference here is whether things are supported in core Postgres or whether you have to write them yourself. Obviously, if all you do is open the manual at page 57 and it tells you to use a function, then that's cool. If you have to write it yourself, it takes time. So clearly every release is going to have more and more things within it, but there are always going to be things that you need to add specific for your application in order to make it work. So these are not blockers to you using Postgres, they're just things that require a little bit of attention for your specific implementations, okay? So that's really another illustration of the power of Postgres because we're supporting user-defined data types, so you can always write your own stuff if you want to. So in summary, please go to Abhijit's talk on locking, please go to Ivan's talk on practical JSON, and please enjoy the rest of the conference. I apologize, I need to leave tomorrow, so you won't see me, but it's been a great conference. Thank you very much for your warm welcome as ever, and I've got a couple more talks, I think, but other than that, see you next year. So, cheers.